Hello, this is Catherine and Esther, and this is the least frequently used eviction algorithm for Basejump STL. So this is an overview of our project and some of our goals and our original approach. So our goal is to develop an least frequently used algorithm for integrating into Basejump STL, which would replace the current least recently used algorithm being used for cash eviction. And we need this because the LRU is space efficient, but it's not always the best choice for performance, especially when data access patterns exhibit high frequency of access. And our approach originally was to combine LFU and LRU algorithms, but we're going to be mainly focusing on our LFU algorithm implementation.
And this is the way we implemented the LFU algorithm. We use a frequency matrix, and we have a module that takes in a row from the matrix at a time, and then um, it just has some logic that finds the minimum frequency and which way it belongs to. And so this is the way we decide which way is the least frequently used. So this is an overview of the algorithm, and this is also how it relates to the cache miss handler. So whenever we encounter a miss, we output the chosen way to be evicted, and then we put that into um, the frequency matrix handler, which is where we update or clear the frequency because we're bringing in new data.
So this is an overview of the design, the testing, and the results we did for our project. So we implemented the RTL for the least frequently used frequency matrix. We also wrote some modifications to BSG cache to be using the LFU instead of LRU algorithm. And then we also generated trace files from regression v2, which is a group of Python files in Basejump STL, and we were able to successfully run traces generated from random1.py and testbyte1.py. We also ran synthesis for the LFU module in BSG cache. And then we also tested the software implementation, which is a cache simulator comparing both of those replacement policies. This is just a simulation output of successfully running one of the traces in simulation. And this is the software implementation of the cache simulator, which is we found was an open source implementation where you could specify the memory size, the cache size, the block size, and the mapping policy, and then you'd be able to do like random reads and random writes, and then specify how many random reads and writes you want to do. And you can also read to specific addresses and write to specific addresses and be able to see the total hits and misses and see the hit-miss ratio.
And these are the two tests we ran on both LFU and LRU. So for the first case, we do random read 200 times, and we did this for 19 trials for both the LRU and LFU algorithm. And then for the second test, we did a synthetic benchmark, which we designed the test to read from 500 addresses and then read from the same address, which is in this case 30 and 1 for 600 times. And then we alternate between random read and reading from address 30 and 1.
And this is just some tables of the simulation results from test one showing the percent hit slash miss ratio. And then this is from the second test, and you can see right here the hit slash miss ratio in the tables.
So this is a comparison between test 1 and test 2. In test 1, we did 200 random reads, and in some cases, LRU performs better, but overall, we observed that LFU performs better by about 1%. And then for the synthetic test bench that we designed, the LFU performs significantly better, which is around 2.5%. Some future work that we're planning to do is to push the LFU algorithm through the entire flow, which includes par and then sim par to check the functionality. And then potential work to be done is moving window on the LFU algorithm or even set dueling between LFU and LRU algorithm. Thank you.